morning, everybody. If we are ready, we're happy to start. Good morning. First, I would like to thank the organization, AFA and OMIFCO, for giving us the opportunity to present Stami Carbon technology and some of the corrosion experience we have over the past years. My name is Mike Jordan. Started Stami Carbon this year, in January. Before that, I've been commercial director of the Christoph Group, where SBN is one of the well-known companies in urea fabrication. And before that, I worked at Sandvik for quite a while, and been more or less very much occupied with the development of the Safrex material and also the latest Safrex developments, which I will show you later. I also have to apologize, Mr. Kirk Offey, who's supposed to give this presentation today. He couldn't make because the Dutch authorities didn't get his passport back on time. He's applying for Dutch citizenship and he didn't have his passport. So last Friday they asked me if I could also do this presentation. He is our corrosion specialist, so much more knowledgeable on that aspect than I. So please give me a little bit of time in that respect. First I'm going to show you in the presentation some of the corrosion issues in urea plants that are non-Safrex. And after that I will show you a little bit about the corrosion issues in the Safrex plants, because you know our technology is based on equipment, high pressure equipment made out of special developed material. And after that, I will give you a little bit of insight of the new developments in Safrex, because we have a couple of new developments in this area. First, I would like to show a little bit about our process. This is what we call the 2000 plus technology, where we have 4 pieces of equipment. The high pressure stripper over there. We have a pool condenser, high pressure scrubber and a reactor. This is one of the most common used technologies we have. We have developed also in that, and our latest technology, for instance, what we call 5XX, is a technology where we have a very low energy and low steam consumption, below 600, and only requires 2 pieces of equipment. So if you're interested, we are happy to inform you more about that. Typically runs on 145 bar in the high pressure synthesis part, and temperatures around 183 degrees centigrade. Here you see a 3D modeling of the setup of such a plant. If you, for instance, look at the 5XX, what I just mentioned, the elevation of the plant can be a lot lower because it's only required 2 pieces of equipment, and we are, I think, around 24 meters height now for when it comes to the elevation of the plant. Now, corrosion challenges in the urea plant. We all know that the ammonia and the CO2 as itself are not so much corrosive. Also, the end product is not so much corrosive. But the synthesis, the process as itself is, the carbamate is extremely corrosive. And in carbon steel, it has, let's say, we can say that it has a corrosion speed of 900 millimeter per year. And if something goes wrong, you can have severe explosions, and this is a result of a small plant that exploded some years ago, and we don't want that. So we have to do something about the carbamate, and that is the biggest issue in in the urea plant. An overview on how combating the corrosion in the urea plant. In the 1960, the common material was 316 urea grade, required an oxygen passivation. This oxygen passivation actually was discovered by Stack, that if you use oxygen to passivate, it could make the urea production possible on a larger scale. So, but yeah, we found out that this material was not enough, and we, together with Sandvik again, started to look at better materials, and we together came with the 25-22-2 material. Unfortunately, at that time, nobody was so clever to patent that, but it was an invention again of Stamicarbon together with Sandvik. And the corrosion resistance of that material was a lot better than the 316 UG. And in 1996, we developed a total different material, a duplex material. And actually, with that material, no oxygen was really needed for the passivation because of the structure of the material. However, not any plant was running on zero oxygen, but it's good. Some of the design requirements. When using the austenitic stainless steels, it is, let's say a must that there's no crevices in the fabrication. That there is a leak detection system. We recommend leak detection systems on all equipment, because once you have an issue, the leakages will be detected, and then you can stop the plant immediately. And also thermal insulation is extremely important because of the condensation corrosion, which is a bad type of corrosion too. On the fabrication requirements, Stamicarbon has quite high standards to make sure that the fabrication and the equipment is well inspected. For instance, we have, together with Sandvik, we have a supply agreement where we are allowed to come to Sandvik 3-4 times per year and to check on the material to make sure that the material is always at the same properties. Welding procedures, we go to our fabricators and we inspect the welds. We have a final inspection, so we can make sure that the material and the equipment, what is going out, is according to the plans and according to the specifications that we hold.
Which was worse corroded? Is it the material itself or the joints of the welding?
Sorry, say that again?
The corrosion happened to the welding, the joints, or to the material itself?
So corrosion happens to the carbon steel, which is protected by some line-off suffrates.
Yeah. Yeah, thank you. Also, heat treatment is very important. We saw yesterday also showing that post-weld heat of the heat treatment of the equipment is important, which is also for the equipment. And of course, the water quality of the hydrostatic testing is important. So it needs no chlorides. And some other issues to combat. Transportation requirements. When you supply equipment, non-Safrix equipment, it is required, or actually, yeah, it's required to have nitrogen blanketing. We have experiences in that when supplying equipment in an open top vessel, that contamination of chlorides attack the equipment. Some of the operational requirements, the oxygen content is important, passivation air. For the austenitic stainless steels, it is very much needed. As I said, chloride contamination. Turn down ratio is important, blocking in time, and also the startup procedures and the startup rates. For these operational requirements, this is extremely important for austenitic stainless steels, but it's a lot more important for Safrex. I would say 90% of these are not an issue at all with Safrex material. Then inspection and maintenance. We have risk-based methodologies that we require, so we make sure that all the inspections are done. For instance, what we have is that if we see for austenitic stainless steels, we have inspection intervals of 3 to 4 years. We have now experience with Safrex that we can extend the intervals to 4 to 6 years, which of course is a big cost saving. Well, here again you see the carbamate corrosion. When it's passive, it's about 0.051 millimeter per year, but when it gets active, it goes 100 to even 1,000 times more faster, which immediately creates an issue. Here we show where is the issue in the urea plant, and it is always not only with the stomach carbon process, but with all processes. It is in the stripper, especially when you start up the process. It's getting critical because when the temperature goes up, also the partial pressure of the oxygen goes up. And so you have, let's say, the highest partial pressure and the lowest partial pressure and the highest temperature. So you can see here in this area. Does it work? No? Well, yeah, anyway, you see it here. No, right. This is the area where the issue is biggest. Oh. Yeah, okay. And that's why the stripper is the highest risk of having severe corrosions. Another element that is contributing to the corrosion is of course chloride contamination. We all know that this is an issue, especially in the Gulf area where the chloride content is high, and that is something that is relatively difficult to attack. Yesterday I had a discussion. This is something outside of the urea, that the cooling through seawater cooling is an issue here. And most of the time, materials like titanium or alloy 625 are used in this region. I would like to, with my background of Sandvik, I would like to give you consideration that there is a very good hyperduplex material that could be an extreme good substitution, but also cost-wise it would be very interesting. So there is more materials to attack these chlorides in the seawater cooling. Also another issue is the sulfide contamination. Sulfide binds to the oxygen, which then reduces the oxygen passivation, and could also be an issue with the austenitic steels. And both of these are not an issue for a duplex material like Safrex, for instance. Here, there's an overview on the typical corrosions in the high-pressure equipment. On the left, you see a high-pressure stripper, a carbamate condenser, or the high-pressure scrubber. And on the right, there is the reactor. And there you can see a scheme of where these corrosions are more or less apply. And we have crevice corrosion, stress corrosion, cracking, condensation corrosion, stain-induced intergranular attack, and stern phase, also known as cross-cut end attack, the active carbamate corrosion, and under deposit. So I'll go through a little bit on the issues in the austenitic. If we take the crevice corrosion, I will show you an overview. That's most of the time at the top and the bottom, where the gaskets are at the manway covers. Here you can see a picture of a manway hole where there was a gasket and a crevice appeared, and after the corrosion or the carbamate entering in the crevice, you could see the crevice on the flange face was heavily damaged due to this corrosion. So it is very important to avoid all crevices. The condensation corrosion. Condensation corrosion is actually a very dangerous corrosion because it is something that is coming from outside. If you don't have much control over it, and it's very difficult to avoid. So you have to really be careful what you do with that. Here you can see a construction of a vessel where the vessel was insulated, but they forgot to insulate the lifting lug. You can see in the middle lifting lug, there was, due to the condensation corrosion, the inside of the vessel, you can see here, corroded heavily. So when you have these kind of, let's say, extra material to the vessel that is really not needed for the process, we advise to take these away. This lifting lug could easily be cut off because you don't need it, or you need it in a long time, and you can make a new one. So take these away. Don't keep them there because they are, they could cause a problem in your vessel. Stern phase corrosion, cross-cut end attack, also known as, is of the heat exchanger tubes, is an issue. Here you can see on the right, no, on the left, there is this is a 316L UG material. On the right, there is a 2522 material. I will come back to that, but this is an issue which occurs. This is also an issue with Safrex because it is. It has to do with the manufacturing process of tubes. It's longitudinal, so you will always have, if you cut it like, if you do the cross-cut, you will always have a structure that can create a stern face or cross-cut end attack. This is, this is not, I mean, this kind of corrosion is not good, but it's not like really creating severe and dangerous issues. The passive and the active corrosion. You can see here temperature from above, 183. Here at the stripping process in the middle approximately, the temperature goes up to around 205 degrees, and at the bottom it's around 175, 73. So there is a difference in temperature in the stripping process, which which creates a higher passive corrosion rate. And when there is no oxygen, so when you have, for instance, a stagnant situation, and there is no oxygen, you will get active corrosion, which means that when you have the materials that are really cannot stand the active corrosion, it will go very fast. Yeah, so here you can see an example of a tube in 2522, where there was a stagnant condition, active corrosion occurred, and within 8 days there was a tube rupture in this. So you can see that is very important not to have. Yes? Can you give the mic, please, to?
How can I repeat corrosion in the top of the reactor, urea reactor flange?
How can you?
How can I repair corrosion in urea reactor flange?
How you can avoid it?
Repair.
Repair.
If there is a corrosion,
Yeah.
how can I repair it in the top flange of the urea reactor?
What kind of material you're talking about? No?
How deep the corrosion in the top of the flange of the reactor?
Yeah.
How deep the corrosion?
How can I repair it? There is a corrosion in the top flange of the urea reactor. The material is it was 360.
316, yes?
Yes.
Uh-huh.
How can I repair it?
Repair it?
Yes.
Yeah. Some of them can do weld repairs on that, but then you have to be be very well secured, of course. But I would not know how people repair that, to be honest. But I think some of the times the welds are or let's say the corrosion is taken out and there's a weld repair to that.
May I answer?
Yeah.
We have done the flange phase, I guess, at the reactor, yes. And we do, of course, the grinding, cleaning, weld repair, and then you do machining with special machines because you need a complete new surface there. That's it at the moment. Yeah. If it is a much deeper corrosion, we have a problem.
Then you have to replace it, yeah.
But this is really a bad corrosion. Normally it's only at the gasket surface, as I have learned.
Yeah, correct.
Does it help?
The condition of the corrosion is very deep, can't repair it. It should be replaced.
Yeah, then you have a problem, yeah.
Yes.
But normally you see leaks before, yeah? It will not go so much.
Yes. Okay. Okay, then we're going to go to the Safrex material. When you're using Safrex, actually, this is where you had the scheme, and here you can see that more or less all corrosion issues are gone, more or less gone, with Safrex, using Safrex. The only one that stays is the crosscut and detect. As I mentioned before, that this is an issue because of the production process, which cannot be avoided. But crevice corrosion with Safrex material is not there. Stress corrosion cracking we don't have. We have seen over the past, 25 years, no active corrosion occurred, even in stagnant conditions. I will show you some pictures about that later. So Safrex is really helping avoiding corrosion issues in the equipment. So to give you an overview on the Safrex superior properties, passive corrosion rate is less than 0.05 millimeter per year. for the liners, weld overlay in the tube sheet, the overlay in the hemi heads, the heat exchanger tubes. We haven't seen any crevice corrosion, no condensation corrosion because Safrex doesn't really need oxygen. As said, no active corrosion. We don't see any under deposit corrosion. We had some corrosion in heat effective zone areas of the liner welds. That is because welding Safrex is critical. That's why we are so very keen on inspecting the welding methods of Safrex, because heat input has an effect on the ferritic part of the Safrex. So that's why it's important. As said, cross-cut end detect, that is an issue still. That is something that we cannot avoid. Well, we have something now which would help, but I will show you later. But that is an issue. The passive corrosion in the high-pressure stripper, we were actually hoping that it would be better than now, but we see now at the moment that the corrosion rate ranging is similar to the 25-22 material, which is for us a little bit disappointing because we were expecting better. However, still, the advantage of Safrex is that it will never turn active. So even though the corrosion resistant is similar to 25-22, still it is a much better and safer material because it will never turn active. Also there I will come back because we have also solved this issue.
Maybe I can ask a question, please.
Sure.
We know that the 316L, then you go to 316L, what you call it, modified, and then now to Safrex. Most of the people who has the HPCC, the high pressure carbonate condenser, they have a problem on the water side at the top of sheet, tube sheet, and we say that we are limited to 4 ppm of chloride. How, if we change the modified, the 316 modified to Safrex, is it I mean, can resist the chloride corrosion?
Yes.
And it's improved in that way?
Yes, absolutely.
And to what extent the chloride can be moved?
I have to know exact ppms because I don't know exactly, but for sure this duplex material, Safrex, is a material that is resistant to chlorides. So that will not be an issue. The only issue that could create, or the only thing that could create an issue is the height of the temperature. But in that case, I don't see in the HPCC, the temperature is not a real issue. So I would say that the Safrex material would definitely be resistant according to chloride. Yeah. To continue and to conclude, it's like we have a preservation error of 0.03, which is proven, but we also have 3 years experience of a plant that had an issue, which they didn't know, and they had a 0.01 volume of oxygen. So the oxygen content can be very, very low. And again, you see that we were a little bit disappointed about the corrosion rates of the in the stripper, and there we have developed a new Safrex grade that should solve that issue too. Okay, this is for this part of the presentation. If there's any questions, please feel free. Okay, thank you.
Probably I have a question again. I just want to
to get the workshop going on, right?
People are always in that land. We concentrate and say, look, you have to make the water, the drinking water, less than 4 ppm of chloride. But in the analysis of the chloride, there is a problem really to fix the limit to 4. If you tell me now the suffix from what time you have started suffering, because everybody know the problem of the HPCC after 10 years of working. So everybody wake up on their HPCC. I think anybody here on the site has an HPCC of 10 years old.
Mm-hmm.
It has changed it because of the corrosion due to the chloride. Is there a means to control and to keep a ppm less than 4 and give an indication that can be to assure quality of water of chloride?
Well, I cannot tell you that because I'm not a process guy. So I have to write it down. Maybe the guys from Oude can help us there, but because they are one of our, yeah. Would you know this?
No, we wonder a little bit because we do not have 4 ppm chlorides in Demmin water, which is used for steam production. I guess you mean the steam inside the stripper coming upwards in the tube, or where do you have the chlorides?
No, you know, in the HPCC, you have water side and you have the carbonate side. Yeah. And at the bottom of the HPCC, you have water. Then it starts to change to steam.
Yeah.
At the top of the flange, you have steam and with a chloride, which attack the tubes from outside and making a cracks.
But with the stomach carbon process?
No.
I'm talking about stomach carbon, exact HPCC of stomach carbon before they change to pool.
Okay, yeah, because we don't have that.
Because we did not face it, yeah. We have plants in operation more than 10 years and never heard about such kind of problems with chloride corrosion in, for example, CAFCO plant, CAFCO 3, CAFCO 4, so on. That's a little bit new, but I would learn a little bit more on this besides in the workshop later on, because even more details, that is very interesting to know.
And it's only on the it's only attacking the tubes, or also the tube sheet at the
No,
at the
it's
top?
attacking start attacking the tube.
From the outside.
From the water side.
Yeah, from the water side.
And then you have a crack at there, carbamide, a leak of carbamide, and from the carbamide it will attack the tube sheet, because the tube sheet is lined from the top, but from the bottom side of it it's a carbon steel, and it will be attacked even the tube sheet at that time. I think in our companies we have at least, to my knowledge, 20 years ago, we have at least 4 or 5 plants has changed their high pressure condenser, carbonate condensers. Kuwait they changed. First year they changed their CAFCO, they have one, they have changed part of it. I don't know who else. Iraqi one has been changed. That's to my knowledge. So I suppose with sufferings we will avoid that.
For sure that is.
More resistant to chloride. But to what extent, I don't know. But even in their lecture, I did not find to what extent is that chloride ppm.
Yeah, then I have to look again at him because he has maybe the figures of the resistance to chloride. I have also not the numbers in my...
No, I have to check that because...
But this can be answered maybe later on as well,
Yeah. But for sure what we know, for instance, is what we are doing now. We are replacing 2 vessels now that had HPCCs that had corrosion issues. One is a Toyo plant as well. So we're replacing that for Sufrex where, we more or less say that this should not be an issue with the
I
chloride.
think you have changed to the pool condenser because of this issue. This is to my knowledge.
Yeah,
I
partly.
left that business 20 years ago,
Mhm.
but I think you changed the HPCC into pool condenser
Yes.
because of that problem.
Yeah, maybe it is, but also, yeah, from a capacity point of view, I would say. No.
Excuse me.
Yeah.
What is the material we use in welding suffix?
What is the material used?
In welding suffix.
In holding suffix?
Welding.
Oh, welding. Well, suffix too. It's welded with suffix. Welding. So the material you weld with is also suffix.
Suffix?
Yes. Which is a super duplex. Yeah. But it's a super duplex with with special salt and pepper, so to say.
Steaming carbon is the only supplier of suffix?
Yes.
Or
Yes.
there is another supplier?
No, we are the sole supplier. Reason for that is that we have done, and I will show you later in the next presentation, of course with Safrex we have done investments in making material. Also now we have invented a couple of new things, so we are investing heavily in together with Sandvik. So we are sole supplier of that, yes.
Thank you.
More questions? Okay, then I'll go on to the next. First, I'm going to show you a little bit of our experience over the past 20 years using Safrex, because Safrex is already 20 years in operation now. Here you can see the forms of corrosion in the ureas in austenitic stainless steels, where you can see it as actually what I showed earlier with the scheme of the vessels, that you have all these kind of corrosions in the equipment made by in austenitic stainless steels. Here an overview of the experiences we have with inspecting. We're inspecting a lot of our plants. We are doing, depending on where and what, 2, 4, or even 6 years intervals in inspection. This is actually it's more than that at the moment, because the inspections are getting more and more asked by the customers for us to be done. First, showing you some comparisons. If you look at this one, this is BCO1 we call, which is the 316 modified grade. BCO5, for the ones who don't know, is the 2522. This is stomach carbon names, confusing sometimes. But here you see, let's say, a typical surface attacked by corrosion in these two materials. This rough surface and a brownish color with the typical corrosion rate of 0.10 to 0.15 meter. This is a underweld defect in 316 modified. What happened here, you see there was a pore in the weld, and this pinhole created a stagnant condition. So the carbamate was there was no oxygen, and was going all the way through, and created quite heavily active corrosion. And you can see on the left there, that is this is what happens when you have that kind of problems. We had the same.
What do you mean by short time? Is it 1 year, 2 years?
Sorry?
What do you mean by short time?
Really short time, like a couple of weeks. Yeah. Once the active corrosion occurs, then it can go extremely. We have experiences of sometimes 8 days. It goes all the way through the carbon steel. Yeah. Here you see a liner plate on the top of a channel of the HPCC in Safarex. And also there was a pore, a pinhole, you can see on the right. So we saw that with an inspection that there was a pinhole, and we did a investigation with dye penetrant, and we checked if there was any corrosion, but there was not. So this shows that even when there is a pinhole in Safarex, it will not create an issue, because it will not. The Safarex will not require oxygen, so it will not. The corrosion will not go any further than it is. Here, another example of condensation corrosion of a top cover, also based or due to bad insulation. And also there, it shows like that there is something happened, but there is no signs of any condensation corrosion when you take away the layer. This is an example of a stripper. Manhole was leaking due to this is the flange face, where it showed that there was corrosion on the Safarex. You can see there is corrosion on the Safarex part, which was actually strange to us. So what happened is that we took away the corrosion, and then we saw that there was no corrosion on the Safarex as itself. But what happened is that there was a gasket that was leaking. The gasket was made out of 316 with a Teflon envelope, and because it was pressed too hard, the Teflon envelope broke, and the corrosion occurred by the 360 material. So when we took away that corrosion, so we could just grind it off, and it showed that there was no corrosion on the Safarex, despite the leaking flange. So we changed the flange or the gasket, and the problem was solved. Stress corrosion cracking is an issue also, of course, in the high pressure carbonate condenser. With the normal materials, the 25 or the 316 modified, or the 2522 material, and we have faced no stress corrosion cracking in carbonate condensers, even despite the higher chlorides. I will get you the information though. This is an example of a tube rupture in a high pressure stripper in 2522. Here you can see that the tube ruptured after 8 days. The reason we found out later was that this was actually 8 days after startup again. So the maintenance was there, and after 8 days, one tube ruptured. So that was quite strange. So we got back, they asked us back what's happening, and then we found out that in this tube, this one tube, a piece of the brush that they used for cleaning the tube stayed in the tube, which created a stagnant condition and created an automatic active corrosion after 8 days. Here we have another example of high pressure SNAM design plant, where the inlet had the tubes were flooded in the inlet of the tubes. And that was a plant where we had a SNAM plant where Safrex was in. And you can see here on this side you can see that the tubes were flooded all the way down, but no active corrosion was seen because with the Safrex material. And this, if you would have another material, this would have created an immediate problem. But because Safrex does not need the oxygen, it stays still very well. You have a question?
Yeah, I just hear that there is a piece of the brush. Is it a galvanic corrosion?
Sorry?
Does it cause a galvanic action on the, so that there is a corrosion there? I mean, there is a piece of brush, as you say, one hair of the brush is in there. Does that cause a galvanic action corrosion, or how it happens?
Well, because there is no oxygen and there is no flooding in the tubes, it creates, the passive corrosion goes to active corrosion, and that's creating the issue. No. Here you have Safrex internal bore welding and an overlay. And after six years effective on steam time, we did the first inspection, and no visible corrosion is seen here. Just some examples that shows that Safrex in operation, 20 years of experience, is performing very well when it comes to attacking the corrosion issues. However, as said before, still we had some issues in the we see some issues in the high pressure synthesis. So together with Sandvik, we gone to get to the table and said, okay, well, how can we improve? We want to have enhanced corrosion resistance at higher temperatures, because we see that the Safrex material was similar to the 2522 material when the temperatures gone higher. Also, we see that when we were talking to, for instance, replacing in a SNAM plant, Safrex in a SNAM plant, it becomes critical, because the temperatures in the SNAM plant are typically higher, so we had some challenges there. So we wanted to have a longer lifetime than the current material. And I said also we wanted to have a material that is suitable for thermal stripping plants. So what we did, we started an R&D program together with Stami Carbon, and we wanted to improve, we want to find material that has an improved corrosion resistance. And Sandvik took a very broad matrix of different experimental alloys. And what we did this time, actually compared to the first time we started with Safrex, is that we bought an autoclave equipment, and we did corrosion screening in the carbamate solution on highest temperatures, which is different because at that time we did not have access to these kind of knowledge, and now we had. So the new alloys were all tested in an autoclave environment with in a real operational carbamate solution. We also wanted to have equal or even better mechanical properties, and of course an improved structure stability, and the weldability should be the same as it is. So these were the starting points. And that resulted, after a couple of years investigating and developing, in a new Safrex grade, which we call Safrex Star. This material is exclusively for the heat exchanger tubes in the high pressure stripper. It's a high alloyed duplex stainless steel. It has optimized corrosion resistance to the carbamate corrosion resistance. Sorry, it maintained its good weldability. It has a higher mechanical strength, and also the structure stability is very good. And here you can see some of the tests. Actually, what we also found is that Safrex material is a very good investment or investigation at the time. I mean, Safrex was in all these more than 10 difficult or different alloys. It was a material that was really, really good in the carbamate solution. Also in the autoclave, because we used, of course, Safrex also now in the autoclave environment. But there was 2 alloys actually that came out better, and one is the one that is the Star. Gives corrosion resistance that is approximately 10 to 20% higher than Safrex. So which means that we can increase the lifetime of the high pressure stripper. And a total production run and Sandvik has been done, and we are doing some field tests at the moment. But it definitely has an excellent corrosion resistance against localized corrosion. And you can see here on the right the difference in the between Safrex and Safrex Star, where you can see that we have done tests in this environment. We have done tests in 205 degrees centigrade, 14 days, in an oxygen-free environment. So without any oxygen, we came to these kind of corrosion rates, where you can see that the 2522 has, in this environment, 20 times higher corrosion rates. Here are some of the mechanical strengths, mechanical properties. You can see that the mechanical strength is better than the Safrex, which means that you can you can have thinner walls, for instance, if you would like. So, regarding Safrex Star, as said, it will only be used in the high pressure stripper tubes, because that is where that's where we really positioned this new alloy, because we had we were not satisfied about the results of the Safrex, and we made the improvements based on that. It provides a definite and considerable longer lifetime of the high pressure stripper, and you don't need to make any changes in the design or the fabrication. Full-scale true production is qualified at Sandvik. The PMA and PED acceptance is ongoing. We have now the TÜV application is approved now. We have a tube, and the SME code case is ongoing, and we expect that to be ready early, let's say in the first quarter of 2018, which means that then the material is also available for to supply to the SME code case. But the TÜV is already there. Then our second new development. As said, we had an issue with the crosscut Entitech, so we wanted to have something that could solve that problem. We also had a problem with some of the components, like the big valve blocks or the ejector, where we had a design temperature of minus 35 degrees, mainly caused by our friends of Oude. in the US and in some of the areas there was an issue. And because of the production process of Safrex at Sandvik, we could not achieve these kind of impact values with the in the material. And that caused sometimes some issues. So we had to find a solution to that. And then Sandvik, they bought a company that did powder metallurgy by hot isostatic pressing, HIP. So they make steel from powder. And every grain of powder has its mechanical and chemical composition that is under high pressure and under high temperature pressed together, so you get a solid solution. And here you can see the structure of the material. This is, let's say, the non-HIP material, extruded, and you can see that this is why there is one of the issues. You can see the longitudinal structure of this material, which creates, for instance, the cross-cut Endotech. The hot isostatic pressing on the left, you can see a very, very fine isotropic structure. It has a very fine and very fine, the austenitic spacing. Austenite spacing is 14 compared to the to 60 for the forgings. So the structure is very, very, very good and different. Which, for instance, we had so that's we have now we started the commercial production. Where we had the first products commercialized according to the AD, 2010 PAD. We had an ejector and some check valves that are produced out of HIP. And HIP, the advantage of HIP is that you can produce near net shape. So you don't need to have, you can make, for instance, if you're looking at the valve normally is produced out of a block. Only this block is forged in the past. And then the valve manufacturer drill the holes, they weld the flanges, etc. With HIP, we make a product that has the valve. This is already there. The holes are already there. So that means that the whole production process is different. It's near net shape, so reducing the machining times, but also, giving us the opportunity to make material or product that is according to the specifications with the, for instance, for the impact values. For instance, if you look at the ejector, problem was there that the holes are so small, and when you have a bigger one, and normally this was made out of a bar, so they drill the holes and inside of the core of the material, because we could not reach the values because of the production process. And now we create. We make an ejector with already the hole in it, so the issue is gone with this material. Another issue was with the cross-cut Endotech. In the liquid dividers, the ferrules, we saw that after time the holes, because of this cross-cut Endotech, became larger and larger. And we could not do anything about it, so we tried all sorts of things, weld, do all sorts of things, but it was not really what we wanted to do, what we wanted to have. Here you can see, this is, let's say, the microstructure of the Safrex, the normal Safrex, made out of a tube or bar. And you can see the structure on the surface is rough. And because of the composition of the HIP material, you can see on this one that the surface is a lot better, and we don't have any issues with that anymore. So also we can make these ferrules now near net shape, so the machining time and machining cost is a lot less. And the problems are solved. We have now Safrex degree in operation. Actually, it's more than 2 years, to be honest. So, and we don't see anything. You cannot see it now in this, but you can even see still. You can see the drilling, the surface of the drilling. So you don't see any attack on that. So also there we have covered and solved this issue we had with that. So to conclude, Safrex has a proven and excellent performance in the urea plants for over 20 years. We solve with Safrex 90% of all the corrosion issues. And actually we kind of now say that with the new Safrex Star and Degree, we solve 99 of the corrosion issues in the plants. Conclusion: Safrex, the whole family now, because it became a family with the new two developments. More oxygen, more flexibility in your plant operations. Oxygen passivation is not needed. However, nobody dares to run a plant on zero oxygen. But we, with the Safrex Star, we dare to say that we definitely can run a plant on zero oxygen. Turn down ratio is not critical. Blocking in time is not critical anymore. Less inspection, longer inspection intervals. What I said, like we have experiences now 6 years. Less maintenance and repair, of course, meaning lower OPEX cost. Oxygen content, yeah, as said, still design for 0.3. However, we have experience of 0.1%. And that all results in a safer operation and a higher plant yield. Thank you very much.
It is lower OPEX, as you said, but what about the CAPEX? Is it lower CAPEX or much higher CAPEX?
No, it's a CAPEX as you are, let's say with the new materials, you would not see any increase of the CAPEX in total.
What is the difference in the price?
Yeah, it is. You know, it's a bit difficult because if the price, excuse me, let's say the price of the tubes as itself are a little bit higher from Sandvik to us. However, no, but that doesn't mean that also the total price will be more expensive because that is a different approach. Yeah, so we might have a higher, for instance, if you take the ferrules, the production process of HIP is a lot more expensive. But we will not, so the ferrules will not be more expensive, for instance, than the normal process. Yeah? Although the material as itself is more expensive. So that is, so it's difficult to say that, let's say I can tell that there will not be a CAPEX increase due to new materials.
Yeah. So you can say that we can benefit from the lower OPEX and much longer life.
Yes. Yeah. But no increase in. So please. No questions?
I have a question regarding reducing the passivation or the oxygen percentage. First of all, is it, if there is experience, for how long it was tried, and for which percent? Now we are operating in SAFCO 0.6%.
0.6?
0.6.
Yeah.
If we want to reduce it, for how much? Second thing, should we have all HB synthesis loop suffix or only HB stripper?
If you want to reduce the, if you have a full suffix plant, you can reduce it to 0.3, proven. Yeah. If it's not fully suffix, then you change it to full suffix. No, but then you, I would recommend not to reduce it to 0.3 because there you run a risk then.
Okay. Is there any experience? Any experiment, for example, reduced and
Experience are, yeah, I mean, there's a lot of experience that it is not recommended to run with non-suffix material below 0.6. So I would not recommend it. Then I would recommend to change the whole plant to suffix, and then you can run around. Yeah?
we are talking about suffix. Suffix, yes.
Yeah, and you're running there 0.6 now at Safco 4?
0.6 currently.
So yeah, you could reduce, but then I would recommend to discuss this with our process engineers, and then, yeah, it should be possible.
You know, my question, because decreasing the oxygen percentage or inerts will be significantly helpful and
Yeah.
beneficial.
Yeah, but we can, yeah, we can assist you on that if you would like to have time. Yeah. More questions? No? Okay, then I thank you.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, ladies and gentlemen. My name is Yasser Mohammed. I'm a urea shift supervisor working for the GBIC, the Gulf Petrochemical Companies, Industries Company. GBIC is a joint venture between the government of Bahrain and SABIC, Saudi Arabia, as well as BIC from Kuwait. The production of GBIC was started in 1985, producing ammonia and methanol. And in 1998, urea plant was commissioned to produce 1,700 metric ton of urea using SNAM's total ammonia recycled technology. This is a simple flow diagram for the urea plant as run by using SIPEM technology. And SIPEM total ammonia recycle technology, the urea solution. Am I seeing the dot? Everyone, leave it. The urea solution leaving the HB section of the process, having 44% urea, gets decomposed and recycled back through two stages. MB stage, which is running at 20 bar gauge, and a low pressure stage, which is running at 4, increasing the concentration finally to 96 before it is fed to the granulation section of the plant. During the running of the plant for now almost 20 years, the only major issue we have faced was the tube failure of the medium pressure decomposer, which caused us to replace the MPD twice before we finally were able to find a reliable substitute. So I'm gonna talk about our journey, what we did, and how we be able to, well, let's say, it's like a story. We started with a bad thing and we ended with a happy ending, as they say. Simple explanation about the MPD. Our MPD is a standard shell and tube vertical falling film heat exchanger. The solution enters at the top separator where the gases, the flashed gases separated before the liquid enters to the exchanger side. The exchanger side is operated with divided to two parts, where the upper part is heated by saturated steam and the lower part is is heated with the medium pressure steam condensate. The outlet of the MPD containing 64% urea. And at the bottom of the holder, we also have an injection for the HB inerts, the inerts coming back from the HB section. The plant was actually commissioned in January 1998. And to our surprise, after only 6 months of operation, the tube, we faced a tube failure from the MPD. With 6 months only of operation, we suffered a tube failure, which caused us to shut down the plant. When shutting down the plant, we found that 6 number of tubes has been ruptured, which were at the bottommost baffle plate, at the bottom tube sheet. IRIS identified almost 36 tubes that have suffered thickness reduction, and all of these tubes were plugged. Now, after plugging of these tubes, we returned back to service. The only change we did was operate the bottom half of the MPD with only steam. I mean, with the condensate alone, without any steam injection. After almost 20 days of operating, another leak has occurred. This time, 4 number of tubes have been ruptured, almost at the same place. Eddy current survey also showed that almost 75 tubes has suffered from thickness loss. With the eddy current results and with the help of some inspection agencies, it was concluded at that time that the cause of this tube failure was actually external damage to the tubes. And it was caused by the steam bubbles collapsing in that small gap between the baffle and the tube that was causing this rattling and damaging of the tube. Based on this, with the 75 tubes that have been found that have suffered thickness reduction, this was plugged, giving the total now of 116 tubes out of 985. The third, after running for almost 8 months or 6 months, another tube failure has occurred. This time 3 tubes has been found ruptured, but the problem with this time that one of the tubes actually ruptured at the middle of the tube sheet. By this, the top shell side and the bottom shell got connected through the ruptured tube. This has given us a disadvantage in running or restriction in running the MPD while independently without using the condensate. With this, again, the boroscopic examination and eddy current showed another 32 tubes with thickness reduction. With all of the tubes being plugged, this has brought the total of 15% of the tubes that have been totally plugged. At this point, in order to continue running the plant while waiting for another replacement MPD to come, some modifications were done, special operation. One of the modification was to change the HB inert inlet at the bottom of the exchanger to Sparger type to improve gas distribution, as well as some major piping modification to bypass the bottom shell exchanger and to operate it with a slightly higher, operating it with only the top shell side with the slightly higher steam pressure. This posted a lot of restriction for plant operation, but we could at least continue to run the plant at 85% load. The replacement of the exchanger was put on high priority since we found out about since the second leak has occurred. And just when we have found out that the second leak has occurred. But in order to with the consultation with SIPEM and the main contractor MHI, we discussed about some improvement to improve on the exchanger to reduce the damaged or the failures of the tubes. Some of the design improvement at this time was the adding of expansion joints for both the upper and lower sides to eliminate stress-induced vibration. Moreover, the bottom shell vapor belt at the condensate inlet was replaced with an embankment plate to reduce the flashing of the steam. The useful length was for the bottom heat exchanger was also increased from 1.5 meter to 2 meters to offset the reduced number of the tubes. And the tube-to-tube sheet weld was revised from seal weld to strength welds. All of this improvement was implemented on the second MPD. Now, while preparing the second MPD for commissioning and installing, an invasive inspection was carried out on the MPD, the old MPD. This has indicated that, contrary to what we have thought about it being the cause was external damage, it actually was showing us that the damage was mostly from the inside service due to extreme corrosion. Tube samples have been taken and sent to a couple of agencies for testing. It was showed that the tubes actually complied with the standard for 316L, but in terms of reference to the carbon, chromium, nickel, and molybdenum specification or concentration, composition, they were at the bottom end of the specified range for the 316L. Now, with this, before we went with the operation of the new MPD, with the study of the thinning phenomena as well the effects of corrosion and how to reduce the effect of corrosion in our MPD, some of minor changes have been done. One of them was plugging one of the 4 distribution holes in the ferrule, thus increasing the hydrostatic load on the tube sheet. The driving force for the gas flow also reduced by enlarging the gas escape hole. The severity of the temperature also affects the corrosion rate, so we decided to operate the bottom side, the condensate side, at a lower temperature. Instead of 210, we're operating at 187. As well as the oxygen content in the CO2 feed was increased to from 3.35 to 0.45%. The MPD, second MPD was put in operation, and after 2 weeks of operation, we noticed an increase in the iron content at the solution outlet, which has it to 1 ppm, which caused it to stop and investigate the cause of this. When the tubes were examined, 50% of the tubes from the bottom sheet appeared silver shiny. The eddy current examination revealed almost 10 to 14% of wall loss in these 15%. At this time, with what was thought with the SIPEM, through the technical discussion with SIPEM and MHI expert, it was suspected that the corrosion condition in GBIC's MPD was more severe than what the normal stainless steel 316L tubes that could resist. Although this is the same design that SIPEM have been using in number of urea plants and never has been faced any problem. We put the plant back in service, and after 45 days we faced the same issue. The iron content again started rising, and we had to shut down the plant and investigate again. This time, to our horror, we found that 25% of the total tube suffered almost from 0 to 20% thickness loss. 10% of the total tube suffered from 21 to 50% thickness loss. And almost all of the tubes showed, all of the affected tubes showed thinning up to 5 meters from the bottom side tube sheet. Now, with this, further modification had to be implemented in order to increase the life of the exchanger as much as possible till we can get, well, till we find a better solution for this problem or continuing problem. One of these modifications was to replace the ferrules. Instead of a closed and capped top, we replaced them with an open one. Ferrules with 4 liquid distribution holes were fitted. Separator section at the top of the MPD was fitted with a Chinese hat in order to distribute for better liquid distribution. And 71, as a precaution, 71 tubes with over 20% thickness reduction were plugged. We did also some operational changes. The bottom condensate temperature was reduced to 167, and we increased the oxygen content in the CO2 further to 0.55. We tried at this point to increase the lifetime of the MPD as much as we can till we could find a permanent, more reliable solution to this problem. However, the deterioration of the exchanger continued, and we still had increase in iron and nickel content in this. One thing we have found out at that time that although both exchangers, the first one and the second one, was manufactured with different manufacturers, but the tubes was actually sold from the same manufacturer. So that was one of the, well, suspicion that the tubes were actually in fault. Now, of course, the plant was continued to run with the 85% load until a proper exchanger was designed. This time, considering the severe corrosion that took place and wanting to avoid multiple failures again and to increase the reliability of the plant, this time we went for an upgrade of material instead of just implementing some technical modification. We upgraded the material from the normal 316L to the 2522 stainless steel. And some further modification also carried out, like the ferrule hole diameter was decreased. It was decreased to 3.2 for higher liquid, and the top separator was changed with the view to improve liquid head and uniform distribution. Now with this, it shows the couple of changes that was done. First of all, from the first exchanger, we were using condensate plus steam as a boosted steam. But now we are using only condensate at around 210 degrees Celsius. The material of construction, of course, changed to 2522.2, and the baffle or the vapor belt was changed to a baffle type. Some minor design changes in the ferrules, as well as the steam distributors. The third MPD was installed in November 2000. While installing this, we carried out eddy current survey for all the tubes to have a benchmark record. We carried out borescopic examination. We did a thorough inspection of the tube sheets. We checked the equipment verticality check, and we did all the pre-startup degreasing and cleaning, as well as the flushing of both chill sides with steam condensate in order to prepare the equipment for service. Commissioning of the MPD was in 2000. For the first month of operation of the MPD, the plant was operated with a conservative operating condition in order to monitor and to monitor the MPD for any unexpected behavior or unexpected leakage. And the plant was continued to run at 85% load in order to monitor this. We did lab analysis for the exit solution, for iron as well as nickel and chromium on a daily basis until almost remained at almost 0.1 ppm for a longer period, till 1 month. Then after the 1 month operation, we started to increase the process parameters one by one, increasing it on a period of 4 months until we reached the final operating condition and we could run the plant at 100% load. We did this in order to see the effect of each parameter on the process, as well as if it causes direct, let's say, tube damage or thinning, as well as it gives us to test the flexibility of the plant. With this MPD now, the lost MPD now has been running for almost 18 continuous years. It's been through several shutdowns, and we are currently not facing any problem with it. To conclude, this was a new experience to GBIC, as there was no reference point to show whether there was no issues with this equipment from before. And so there was no reference to compare. So GBIC had to solve it in a systematic way, and with the help of the licensor, SNAM, as well as the main contactor MHI, we were able to reach or to solve this issue of the failure. As experience or what GBIC recommends always from this experience is that never underestimate the severe corrosion or the severe corrosion condition of the MPD. And it gives us the right to, the focus or the material of construction, as well as the sourcing of the tube and manufacturer, is of high importance when it comes to this equipment. Because most of people think about corrosion, they think, okay, the HB section, the reactor, the strip bar, and this, but the MP also suffers from works under severe corrosion condition. Moreover, the implementation of the other modification also helped in reducing the severity of the condition. Also, GBIC recommends always to carry out the lab analysis, to always continue monitoring the equipment, and recommending eddy current survey every 3 to 4 years, and to ensure that the equipment is still running reliably. With this, I conclude my presentation. I thank you very much for listening. I'm happy to answer any questions. نعم. Hydrojet? Currently we are doing hydrojet cleaning, as well as we're doing also the chemical cleaning of the tubes for the MPD. We're talking about the last MPD now. Yeah. Yeah, it was normal. Well, no major problem, but the fouling of the tubes is a normal problem when faced with the MPD. Currently, okay, we're having a little bit of problem when it comes to the fouling. We're using hydrojet as well as chemical cleaning in order to remove it. It depends on the tubes, depends on the fouling. How much fouling is there? Yeah. Because of the fouling, it depends. Any further question? For this, I thank you very much for listening.
Good morning again. May I get your attention now? That would be great. I will have today 2 presentations for you. The first one is related to revamp and optimization measures in ammonia plants. And the second one, a shorter one, I would like to introduce to you new ammonia converter loading procedure developed by ThyssenKrupp Industrial Solutions together with our partner Johnson Matthey Catalyst. But I will start with the first one, revamp options in ammonia plants. The presentation is subdivided into parts. The first one is related to the front end of an ammonia plant. That means everything up to the suction side of the ammonia synthesis gas compressor. The second one related to the back end, mainly the ammonia synthesis. And I have one example related to the utility section. It means here, in this case, to the demin water and wastewater treatment. And finally, some words when we get the contract to do a revamp, how we do it, in which steps. Here in my presentation, the targets of the revamp is related to capacity increase, to some measures related to energy reduction, and one example to environmental improvements. Some general experience we made with revamps is that most of the non-revamped ammonia plants have a potential for a capacity increase up to 10 or 15% maximum. Potential for energy reduction in older plants is high, and it's less feasible in modern plants because they already have a low energy consumption figure. Sometimes minor capacity increase can be reached by altering the process conditions. One example for that is an advanced process control system. And another thing we have recognized for revamps is that plants which have been already revamped have a very low potential for further revamps, what is clear, or the revamps are very costly. Some words to the ammonia process offered by ThyssenKrupp Industrial Solutions. We are offering the Uhde ammonia process, and this process is a conventional process. That means with a steam reformer, secondary reformer, and adding stoichiometric process air to the secondary reformer. Then we have waste heat recovery. Yeah, okay, good. We have a waste heat recovery where we generate high pressure steam and a CO shift consisting of high temperature and low temperature shift. CO2 removal system, there we are usually offering two systems, an MDEA system and the Benfield system licensed by UOP, followed by a methanation section, and then the synthesis gas compression. In our plants, it's usually a two-stage, two-casing ammonia compressor consisting of 3 stages and a recycle stage, and an ammonia synthesis loop with refrigeration, ammonia recovery, and hydrogen recovery unit. For plants up to a capacity of about 3,000 tons, we do it with this system. For plants, single train plants with a capacity of up to 4,500 or 4,700 tons per day, we are using the Uhde dual pressure process, which is not shown here, but I come later to that. Yeah, these are the measures I would like to introduce today to you. First of all, it's a replacing of the catalyst of the steam reformer in the ammonia plant. Then another measure is to increase the size of the tubes. Some measures related to energy saving. Then changing some internals inside the low temperature shift converter or also the HD shift converter, some improvements in the CO2 removal system. Then coming to the back end, also there we have some examples how the efficiency of the ammonia synthesis and the synthesis gas compressor can be improved. That is a synthesis gas drying unit, chilling of synthesis gas, an improved catalyst and booster converter, and finally one example related to the water treatment and wastewater treatment. So coming to the first example, that is a feature developed by our collaboration partner, Johnson Matthey Catalyst. They have developed a completely new type of primary reformer catalyst. It's a high temperature alloy foil shaped into a kind of flexible fan. And on this flexible fan, usual steam reforming material is coated. It is very much promising, and it gives a higher activity of the primary reformer catalyst. It allows a higher heat transfer and a significantly lower pressure drop. It can be inserted in the normal tubes of a primary reformer, and this slide shows the gas flow through this new type of catalyst. It enters from top, goes inside this space, and then down to the next element. There are already 2 plants, smaller plants in the US, in operation with this kind of catalyst, and up to now it is working properly. And more details, you can ask, of course, Johnson Matthey Catalyst, which when they are offering this type of catalyst.
This catalyst will fill the tube?
Yes.
So the outer diameter of this
is the inner diameter of the tubes. Yeah, exactly. Yeah. Yeah. Pardon? Nickel? Yeah, it's the same catalyst material as on a usual primary reformer catalyst. Yeah, the pellets. So, yeah. Same material.
And it is designed to the size ID of the tube itself?
Yes, exactly. Yeah. Yeah. But I should mention it has not the same price as the conventional catalyst. Another measure to improve the performance of a primary reformer has already been mentioned yesterday by my colleague, and it's related to a new material which is available for reformer tubes. This is microalloy R, and with this material the wall thickness can be reduced by 18 to 20%, and that gives, of course, a larger inner diameter, and the increase of the inner diameter or the cross-section can be increased by 7 to 8%, which allows you to put in more catalyst and at least to get a higher performance of the reformer. And I have a comparison of this method. Let's assume you want to maintain the capacity at 100%. Then if you replace two cutter cell at the same capacity, your pressure drop will only be 78% of the pressure drop you had before. And of course the catalyst volume is the same. And this calculation is made on the basis that the maximum allowable heat flux of the tubes and as well as the maximum allowable wall temperature will be maintained, and also the methane content outlet of the tubes should be the same, and the same is with the lifetime of the tubes, 100,000 hours. If you replace the tube material to microalloy R, the pressure drop will be only 88% of the former pressure drop, and the catalyst volume can be increased by 7%. Again, maintaining the maximum allowable heat flux and the maximum allowable wall temperature. If you are thinking now about a capacity increase, if you do non-replacement, there is still some design margin in the reformer tubes, and in most of the cases, you can increase the capacity up to 110%, but of course, it will cost you some additional pressure drop. Your pressure drop will be increased by about 19%. Catalyst volume remains the same. If you are going for a capacity increase and you replace the older catalyst by this new cutter cell provided by Johnson Matthey, you are able to get a primary reformer capacity of 120%. Your pressure drop will increase by 9%, and the catalyst volume is the same. Replacing the tube material, you can get 121%, so more or less the same, but your pressure drop will be 123%, and you need more catalyst, 7% more. Of course, you can also invest a lot of money and can do both at the same time. Then you are able to get 125% of capacity. Your pressure drop will be nearly the same, a little bit lower, and your catalyst volume 107%. Yeah, so far to the primary reformer improvements. Any question to this?
What about bottlenecks after downstream primary reformer?
Yeah, that will be the next bottleneck. So that needs to be then investigated in detail. I would also expect that there are some bottlenecks. Maybe 110% is possible. Many of our plants, they are operating above the nameplate capacity. I don't know, MOPCO, where is it working now? At which capacity? Okay, secret. Good. Good. The next modification is related to the low temperature shift, but can also be used for the HT shift. Usually, the catalyst in our low temperature shift converters are arranged in two beds, and the beds are of radial flow, of axial flow. But we have now developed a system where you can replace the existing internals by a radial flow arrangement, and that will give you a much lower pressure drop. The pressure drop will go down by 15% to 85% of the former pressure drop. What is the benefit from it? Of course, the entire pressure drop of your front end will be lower, and you can save some energy on the synthesis gas compressor. In this case, if you just replace the internals of the low temperature shift, you will save about 1% of driving power on the synthesis gas compressor. Coming to the next unit, this is the CO2 removal system. Many plants nowadays, they're using an amine washing system. The plants we have built in Egypt, and these are many, these are in totally 10 plants, and 8 plants of them are of the same design. They are using UOP's Benfield system, and UOP is offering an improved activator. It's called Act 1, and What you get from it is a lower CO2 slip outlet of the absorber. You can reduce the solution circulation rate. We would expect about by 5%. UOP thinks up to 15%. I would expect the truth is somewhere in the middle. So let's say 5 to 10%. Is that what we really can expect there? You have some opportunities to increase the gas throughput through the system. When we are talking about increasing the primary reformer capacity, also there would be the next bottleneck, and we would expect that we can increase the throughput by 5 to 15%. Maybe it becomes necessary also to replace the packings of the columns, let's say to Rushik super rings or similar. And your regeneration requirement will go down also by 5 to 15%. I have to say that it will not be all at the same time. So if you increase the gas throughput, for instance, through the plant, your regeneration requirement will not go down by 5 to 15%. It will also go up. There are two options available how to replace the old activator by Act 1. There are two measures. That is the gradual conversion or the immediate conversion, whereby the immediate conversion is the recommended procedure to replace the activator.
So the immediate conversion, we have to stop plant and to replace it?
Yes, yes.
But gradually you have to increase or replace it online?
Yeah.
So the second one?
The second one is you have to put it step by step over a longer period. Yeah. I think maybe you can contribute something to it. I think it has been also done in MOPCO. And you have chosen the immediate conversion.
We changed it to blind.
Pardon?
We changed it to blind
Mm-hmm.
4 years ago, but we placed in the actual concentration. It's not easy to increase concentration.
Mm.
I think some escape from generation or it's going with condensate, process condensate.
Mm-hmm.
And as you know, the actual not cheap.
No, I mean improvements. If you want to get more out of your facility, it is never a cheap solution. So always you need some investment to get more out of it. And to revamp an older plant means the additional investment per ton of ammonia is not really cheap. But it is cheaper compared to build a new plant with a higher capacity.
What about MDA?
MDA, MDA principle is the ammonia or the CO2 scrubbing system of the modern art, because it doesn't need any passivation. It gives the much lower CO2 content outlet of the absorber, and that's nowadays the best solution. And there are also techniques available offered by the licensor of the Oase White, that is the name of the system supplied by BASF. They have a system also to change a Benfield system to an MDA system.
But I am talking about the cost. Both of you.
Yeah, the cost, I am not able now to say something about the cost.
Yeah, as a case study or detailed study, they said you have to 1.25 drums per month. But now we are adding 4 drums, or sometimes 5 drums a month, and it's highly costly.
Yeah, this might be that it is highly costly. So we are not selling this Act 1. We can only support you in the replacement and supplying procedure, but we are not supplying the Act 1. Yeah. Yeah, this is also an example related to an ammonia plant in Egypt. This ammonia plant here in this example has a nameplate capacity of 1,200 metric tons per day and an urea plant with 1,925 metric tons per day. And it consumes all CO2, and even if it consumes all CO2, there is still a surplus of ammonia of about 10%. In some plants, it is desired to have some additional sales from surplus ammonia, but in some plants it's not the case. And then is the question from where to get the additional CO2 in order to convert the remaining ammonia to urea. And there are different solutions available. Here in this example, we would increase the ammonia plant capacity by 6% to 1,275 metric tons per day and increase the CO2 production to about 16%. And by that, we would have a real balanced plant. That means that all ammonia is converted to urea. And this can be done by operating the front end at a higher load. That is the cheapest solution. And to return the additional synthesis gas or the surplus of synthesis gas downstream, the CO2 removal system, back to the fuel gas system of the primary reformer or package boiler, whatever you have. And that gives you then a balanced plant. There is also another solution available.
So in this case, you mean that the fuel, energy fuel, will be less?
Yeah, of course.
Gas, then the fuel consumption will be less?
Let's say the total energy consumption. Total energy consumption, that means feed and fuel, will slightly go up.
But we are losing hydrogen and nitrogen.
Yeah, but you gain some additional urea. Let's say in total the energy consumption is going down a little bit, but it is really only a little bit. It's not that much.
So it is balanced.
And the plant is balanced, yes. That means all ammonia is converted to urea. And if you are looking to the sales price of urea and compare it with your ammonia, then maybe it makes sense.
6% in Canada.
Yeah. Yeah, as I said, there is another option. If you need significantly more CO2, then there are solutions available to recover carbon dioxide from the flue gas of the primary reformer. That is also an amine washing system. And there you have really sufficient capacity on CO2 to recover from the flue gas. If we compare these two solutions, means in the first case, with this backflow of synthesis gas into the fuel system of the ammonia plant, of course, you have to increase the capacity of the front end by 16% in this example. It also means some modification on front end equipment might be necessary. You will have an increased consumption of natural gas, that was your question, but it's not that much. And of course, also utilities, electric power, cooling water, and so on will go up a little bit. In this example, what I have shown, this is repeated here, capacity increase in the front end 16% and 6.3% in the back end will lead then, in this example, to a balanced plant. The other option, recovery of CO2 from the flue gas, there are different licenses available. Beside ThyssenKrupp Industrial Solutions, there is Alstom, there is BASF, there is Fluor and MHI, which are offering this system to recover CO2 from flue gas. It has not necessarily to be from the flue gas of the primary reformer. It can also be a package boiler or any other combustion unit. But also this is, compared to the other solution, very much costly. You will not gain additional ammonia. You also have to produce additional ammonia, and therefore also your natural gas consumption will increase. Also utility consumption will increase. Chemicals will increase because you need additional chemicals for this scrubbing system. In this example, to increase the capacity of the urea plant, you will need 126 kilomoles of CO2 recovered from the flue gas. Yeah, that is again a comment. The left solution, option A, is feasible for a moderate increase in CO2 production, and option B is more feasible for larger increase of the CO2 production capacity. Oops, that was the wrong button. Yeah, sometimes also the synthesis gas compressor is a bottleneck when you are thinking about capacity increase. In some plants, you have spare capacity on the refrigeration compressor because very often refrigeration compressors are designed to supply all liquid ammonia at minus 33 degrees to the ammonia storage. But if it is an ammonia urea plant, then you usually supply warm ammonia to the urea plant, and the refrigeration system is operating in partial load. And you may use this additional capacity to install or to chill the gas between the stages of the synthesis gas compressor. We do this in some plants where we chill it down to 6 degrees. And assuming that it was without chillers 36 degrees by cooling water, and if you lower the temperature to 6 degrees, you will gain about 5% additional capacity on the synthesis gas compressor. That can help you. Yeah, this is an ammonia synthesis loop of an Ude plant, from the Ude process, here with a 3-bed radial flow converter followed by an HP steam generator and gas-gas heat exchanger water cooler, and cold exchanger we call it, and a chiller and an ammonia separator. Usually we feed the fresh make-up gas at this point. That means immediately before the ammonia separator. Why we do this? I think for ammonia colleagues here it is clear, because there is still some water in and it will be caught by the ammonia condensed there. That is the reason why we put it there. But it also has a disadvantage, and the disadvantage is that the concentration of ammonia here, which is going from here through the recycle stage of the compressor to the inlet of the converter, is higher, has the concentration according the pressure and temperature here in this vessel. But we have to do it because of the remaining water in the system. Therefore, a really easy installation and not that expensive is the installation of a synthesis gas drying unit. Slowly. We come to this point. Yeah. If you install a synthesis gas drying unit, here in this example it is located at downstream the first stage of the synthesis gas compressor, you can shift the connection point, the tie-in point of the make-up gas from this point to this point. And by this, you can introduce this ammonia-free gas directly to the inlet of the ammonia converter, and that reduces your ammonia concentration inlet of the converter, and you can get a higher conversion rate. In this example here, you can increase by this measure the ammonia production capacity of the synthesis loop by 5%, maintaining the same synthesis pressure and the same recycle rate. But of course, you can also use it to save some energy. That was your point. Sorry, it is not mentioned here. You can maintain the capacity and lower the synthesis loop pressure. I don't have the figure here by how much, and it depends, of course, on your synthesis design pressure. This is different from plant to plant. What I want to say to this measure, it is really a recommended measure. It doesn't cost that much. It will not affect your normal operating procedure that much. It can be installed in parallel to operation, and you just have to shut down to make the tie-ins. What else can be done in the ammonia synthesis loop? Our collaboration partner in terms of catalyst, Johnson Matthey, they also have one catalyst available which they have developed over the years, and it was basically developed for low pressure synthesis plants. There was in former times there was a process that was called AM5 process that was at that time licensed by ICI, which allows operation at a very low synthesis pressure, below 100 bars. This catalyst has a very high activity, and it can also be used in a conventional synthesis loop. Here in this example, 200 bar synthesis loop. And by installing this type of catalyst, you can get a capacity increase by about 4%, or if you are not looking for a capacity increase, the synthesis gas compressor duty can be reduced by 2.3% because of a lower synthesis pressure. So other measures to increase the ammonia production capacity to a larger extent is the installation of a booster compressor. The booster compressor would be installed at this point downstream the waste heat boiler in the ammonia synthesis loop, where we generate high pressure steam. It is a single bed converter followed by an HP steam generator or high pressure boiler feed water preheater, whatever is necessary in the steam system, and that allows you to increase the ammonia production capacity significantly up to 20%. Because there are also some colleagues from SAFCO here. That is for a single span.
S50? The type of
Oh, sorry, S50 is a topsoil. It's a topsoil designation for the ammonia converters. Some of the attendants here mentioned they have a very high natural gas pressure in the plant. I guess that was you?
Yeah,
Yeah, 70 or 80 bars?
around 80 bars.
80 bars. What are you doing with this high pressure? Just release it?
Reduce it up to 45.
Ah, so, and the fuel gas down to 5 bar.
Yeah.
Yeah. So that is an example what you can do with your high pressure natural gas. It makes sense to expand it not through a valve. It makes sense to expand it through a gas expander. And in this example here, there was the natural gas pressure much lower, only 45 bar, and together with some low pressure steam, which is very often in plants, you have more low pressure steam than you need because it's the back pressure of a boiler feed water pump turbine or something like this. And here in this example, you can generate 1.1 megawatt additional electric power, and that is related to a 1,200 metric tons per day ammonia plant. I don't know, you said 1,750 is the capacity of your plant, so it would be even more. Yeah, steam conditions. You have always a fixed amount of process waste heat available. And you try to utilize this waste heat in the process to generate usually steam, and of course also to preheat other process steams, but also to generate steam. And you can do this at different pressure levels. And I have some examples here which says it makes sense to generate or to recover process waste heat into steam at a high pressure and temperature level. Here in this example, we had assumed in case A, there is a system where it is operated at 108 bar and 505 degrees centigrade, and you get from the process, from recovery process, recovery of process waste heat, 100% of mechanical power if you send it through a turbine. And if you would increase it to 113 bar, 535 degrees, you already get 1.7% more mechanical power if you use a steam turbine. The case B is related to very old plants. They are recovering process waste heat at a very low pressure and temperature level, 50 bar, 410 degrees, I have seen very often in older plants. Also, they just get 100% of mechanical power from it. But if they would introduce a steam system with a much higher pressure and temperature, here in this case 113 bar, 535 degrees, they could improve the efficiency significantly by 16.8%. And very often we are asked from owners of very old plants, why is my energy consumption so bad? We have more or less the same equipment as in a modern plant. We have a hydrogen recovery system, and we have all, but our energy consumption is at 8 or 9 gigacal per ton of ammonia. And that is one important reason for it. And that is because they are recovering process waste heat at low pressure and temperature. That is a steam system of an ammonia plant, of a large ammonia plant, here 3,300 tons per day, and it shows the steam system. On the high pressure steam header, we have the synthesis gas compressor turbine and refrigeration compressor turbine. Both are extraction condensing turbines. And on the medium pressure level, we have, of course, the process steam, boiler feed water pump, process air compressor turbine, and it is an ammonia-urea plant, also a CO2 compressor turbine, and an electric power generator which provides the electric power for both process plants, and a package boiler which balances the MP steam system. This ammonia plant has an energy consumption of about 6.9 gigacal per ton of ammonia, or if you look to the urea plant, 5 gigacal per ton of urea. And 6.9 is already a very good figure. Let me say for modern ammonia plants, 6.9 is almost, if it is a conventional routing, the limit. If you want to go down, let's say maybe it is possible to get 6.8, but that becomes then very costly and it's difficult. But there is a way to reduce the energy consumption significantly, and that is if you replace the package boiler by some other equipment. Let's say if you replace the driver of the, here in this example, the driver of the process air compressor turbine by a gas turbine, and using the hot exhaust from the gas turbine to generate steam, then you do not need anymore the package boiler for continuous operation. Maybe you need it for startup or other things. And the energy consumption goes really down. So for the ammonia plant, if you make the balance around the ammonia plant, it goes down to 6.4 gigacal. For the urea plant, to 4.8 gigacal per ton of urea, which is really a quite low value. Yeah, coming to the last example of this presentation, that is related to the demin water unit and the wastewater system of an ammonia plant. Here in this case, the ammonia plant has a sweet water cooling tower, and the demin water will be generated through ion exchangers. That means raw water is going through a flocculator, then a sand filter, and the downstream of the sand filter, the makeup for the cooling tower will be taken, and it is the feed for the cation, onion, and mixed bed filter. The sand filter needs to be generated from time to time, and also, of course, the ion exchangers and the mixed bed filter, and the wastewater is going to the wastewater system, in addition with the cooling tower blowdown. And from the wastewater system, it will be disposed somewhere, depends where it is. This is a huge amount of water which you need, huge amount of raw water, and you also generate a huge amount of wastewater. Just to give you an idea, an 1,200 metric tons ammonia plant will consume about, together with an urea plant, will need about 500 to 600 cubic meters per hour of raw water, and will generate a huge amount of wastewater while generating the cation and anion exchanges and the mixed bed, and also from the blowdown of the cooling tower. How to improve this? We can offer there a system which is doing the following. This route is the same, and you have your wastewater streams, but these wastewater streams, maybe it needs to go through an additional flocculator, then through a filtration system, fine filtration system, and then to a reverse osmosis unit. And the permeate from the reverse osmosis unit will be used as additional makeup for the cooling tower system. And only a smaller amount of brine is going then to the wastewater system. That can be further improved because you still have some amount of wastewater, and you can also send this to an additional crystallizer, to evaporate this water by using low pressure steam, and then your waste will only be some solid waste without any liquid effluents. Yeah, so summarizing the issue with the wastewater, goal is reduction of raw water consumption. The reverse osmosis technique can recover water and reduce make-up water demand. Wastewater brine impurities are very high and might be above emission levels. Therefore, it really makes sense to reduce the wastewater stream. Zero liquid discharge, very often required nowadays. There are different concepts available, but for all of them, additional low pressure steam is required. Some more electric power is also required, and if this is not intended, then you need an evaporation pond. When we do, as ThyssenKrupp Industrial Solutions, revamps, we do it in the way that we first try to familiarize ourselves with the plant. I mean, for plants which we have built, where we are the designers, it is much easy. For plants where we are not the designer, it takes more efforts, and we will take readings from the plants and we'll prepare a study. And this study, of course, will be discussed with the client, and it will say something about what you can expect from this revamp. And if this satisfies our clients, we will do a basic engineering followed by a detail engineering and equipment supply. And we will do also erection and startup for these modifications. Yeah, that is the first part of my presentations, and if you have questions now to this part, I would like to answer that. Yeah.
Thank you for the presentation. For the LTS radial tube, will there be any change in the catalyst volume of the previous one, axial flow?
No, it will be the same. It will be the same amount of catalyst. And it should also mention that it can be inserted without doing hot work inside the existing pressure vessel. Yeah. And it's the same amount of catalyst. Yeah.
And for the Act 1, any effect it will have on for changing from DA to Act 1, any effect it will have on the process condensate? Because our process condensate is going to the utilities plant for recovery. Any effect for mix or TOC or any of
Yeah, the majority of process condensate will be separated upstream of the CO2 removal system. And that, of course, contains a lot of impurities, which is formed in the low temperature shift. And as you know, with the fresh low temperature shift catalyst, you will get a lot of methanol and formic acid and other things. And but the Act 1 has nearly no effect on the composition of the process condensate, because most of the process condensate is taken from the process gas upstream of the absorber.
Yeah, we are using it for stripping of you can say the process in the gas cooler. At the beginning, we generate steam from the process condensate to strip the CO2 from in the dissolver. So will that affect? Will Act 1 have a difference?
Yeah, we do not recommend this anymore, so therefore it's hard for me to give an answer. We try to use fresh boiler feed water or demin water to do that. So I would say, yeah, it will affect it, but I can't say in which way. Yeah. Any other questions?
Yeah, and if we're going to change from DA to active, it will require shutdown, but
Yeah.
can't we do it online or not?
Yeah, that is the method which is not recommended. That is this gradual exchange. We would recommend to stop, let's say, at least you can keep the reformer in operation and can do this, but I would do it during an annual shutdown or a scheduled shutdown. Yeah.
Okay, sorry, one more question.
Yeah.
About the enhancement of the syngas drying units.
Yeah.
You can go back. That is
Yeah.
yeah. So will the chiller be required for this as well, for the syngas drying unit? Because before there was just the chiller without the syngas drying unit.
There was just a water cooler.
Yeah.
Yeah.
Will it be required for the syngas drying unit or not? The chiller.
If you ask this way, no, it is not required. But without the chiller, you need a larger drying unit because the synthesis gas contains a little bit more water. Yeah. So it will be larger then. Yeah. Any other questions? Yeah. Then I will go for the next presentation. So, successful application of new catalyst loading methods for ammonia converters. You know, these days, two principal methods for catalyst loading on ammonia converters are available. The conventional loading method and the so-called dense loading. I would like to introduce now an ammonia converter loading method which has been developed by ThyssenKrupp Industrial Solution together with Johnson Matthey Catalyst. I will start with some words regarding the so-called conventional loading method and will expose what was our motivation to develop a new loading procedure. Followed by some slides about the development and testing of this method, and finally some examples of industrial solutions with this new method. The question is, why did we work on such a method? Our motivation is, of course, saving of time during catalyst filling. Ammonia catalyst replacement is often on the critical path during a plant shutdown or turnaround, and applying the conventional loading method, the ammonia catalyst is filled in layers, height about 30 centimeters, and then it will be vibrated in order to get a higher bulk density. By vibration, the bulk density can be increased from 2.3 to about 2.8 or 3 kilograms per liter. The target was, of course, to get a continuous loading method and distribution of particles over the entire cross-sectional area of a radial flow converter. By the way, it also works for axial flow converters. And the secret of dense loading compared to the conventional one is that you gave the particles enough time for random orientation before it settles down. And the advantage of it is you get a higher loading rate. Compared to the 3 tons per hour, you can get up to 15 tons per hour. And the bulk density achievable in one step is also 2.8 kilograms per liter. In our example, it has been tested with Catalco synthesis catalyst, with a pre-reduced one and with an oxidized one. 35-4 is an oxidized one, and 35-8 is a pre-reduced one. We have tested two different methods. And it started all with a diploma thesis in the year 2011. And the student was looking for two types. A static head, as shown on the left side of this slide, where we use then 6 static heads for loading, and a single one which is not static, which is rotating. We have tested these methods on a test rig together with our partner Johnson Matthey in Great Britain. And that is the test rig there in Billingham in the year 2012. On the left side you can see the test rig, and the ammonia converter was nearly of commercial size. It has a diameter of 2 meters, and the bed height was approximately 1.5 meters. That was necessary to get really reliable results and to get it also applicable later on for commercial use. The left-hand photo shows the test rig equipped with a static loading head, and on the right-hand photo there is the single loading head with this rotating device. In the test rig we have only used on the left-hand side 3 static heads. Later on in the commercial one we are using 6. And by luck, the video is working now. Okay, that is the loading on this test rig. And you can see the uniform distribution of the pellets. What we have found out later on was that moving the heads is not necessary anymore. You will get some small hills of catalyst, and that needs, at the end, finally equalized by manually. And the other method we have also tested, and that looks like this. The advantage is you have only one loading head. The disadvantage is you have some mechanical parts there, which is maybe not that nice. What we also found out is that in former times, with the conventional method, the loading time was determined by the people who are doing the loading itself with a hose and vibrating this. That was determining the entire loading time. Nowadays it is different. Now the loading time is limited by the people who are taking the catalyst up to the hopper on top of the converter. If they are fast enough, then you can get 15 tons per hour, 15 cubic meters or 15 tons per hour loading velocity. It really depends now on the crew with the crane and transporting the catalyst to the loading hopper on top of the converter. So we also have some successful applications in real plants. I will show later on which plants. There you can see on the right-hand photo the loading hopper. On the left side, the converter with the loading hopper on top. And again, the loading time determined by the crane people transporting the catalyst to the top. It is possible to load all beds inside the converter, and it's not only working with UDE converter, it's also with I don't know which one, possible. Casale KBR converters, I don't know at the moment. Yeah, this is a view from inside the converter, and on the top photo you can see the the loading head with the 6 hoses going down to the loading heads. The lower photo shows a view from top of the converter down to, I think this is the 3rd catalyst bed, while it is loaded. Yeah. Again, a view from down to the 6 loading heads. Yeah. One of the static loading heads in operation. The student found a good name for it. He called it the ring shadow killer, because it is shaped in such a way that there is no loading shadow caused by the form of the loading head. Therefore, he was working a long time on it, and therefore he called it ring shadow killer. It's not possible to load the entire converter with this method. You need, for random orientation of the pellets, you need a falling height of minimum 1 to 1.5 meter. That means the final 1 or 1.5 meter needs to be, you can use this filling method, but you need then to vibrate it and to equalize the small hills you can see here. But that is only for the last 1 or 1.5 meter. Yeah, this is a pneumatic vibrator, what we are usually using for vibrating the final 1.5 meter. And in this plant, we have successfully applied this loading method. It starts with CFI Port Neal, that was a 2,200 metric tons ammonia plant in the US. And down there another plant, also for CF Industries in the US in Donaldsonville, plant with a capacity of 3,300 tons per day. We have done it in 2 plants in Egypt, ENPC 1 and 2. And we also did it in South Africa for Sasol in Sasolburg. Now this slide shows some loading durations, what we can achieve with this loading method. For a 3-bed converter in a 1,200 metric tons per day plant, you can see 8 hours for the top bed, 10 hours for the second bed, and 11 hours for the third bed, just because the third bed is the largest bed. And in a mega ammonia plant, 3,300 tons per day for a 2-bed converter, 9 hours for the top bed and 15 hours for the second bed. And we have also a single bed converter with a very large catalyst volume, 18 hours, and for the 3-bed converter from bottom to top, 16 hours, 14 hours, and 7 hours. And for a medium-sized plant, 2,200 tons per day, 13 hours for the lowest bed and 9 hours for the top bed, and 16 again for the single bed converter. So that's the end of my entertainment. If you have additional questions, I would be happy to answer them.
جميعا. Good afternoon, gentlemen. My presentation will be about design improvement case implemented on steam distributor and a steam saturator drum in SAFCO 2 urea plant. As introduction, SAFCO 2 urea plant with the steam carbon process technology is in successful operations since 1992. In 2009, we started observing loss and thickness of saturated steam going from the saturator drum to the urea HB stripper, which is 12-inch line. This loss and thickness led at the end to steam leakage, which led to plant shutdown. Maximum corrosion rate for piping was 0.64 millimeter per year, and the erosion or corrosion rate for elbows was 2.06 millimeter per year. These are our names, team members. My name, I'm Abdurrahman Al-Dawsiri, process engineer in SAFCO, which is one of SABIC affiliates. And my colleague, Ali Akbar, who is not here today. First of all, this is the flow scheme for the system. This is the saturator drum. Supplying, first of all, it is receiving the extraction steam from CO2 compressor turbine with 23 kg pressure and saturating the superheated steam by mixing with condensate and supplying through this red line the saturated steam with about 19 kg to HB stripper shell side. And this saturated steam is coming back as condensate to the saturator drum. And in the red line was the case or was the leakage. This is the data. Here is the leakage point, number 8, 2001, 2003, 2006, 2009. Here, loss and thickness started. Then, within almost 5 years, this is the thickness became, with corrosion rate 1.4 millimeter per year. Observations and analysis. Since 2009, level fluctuating started in this 18 meter cube drum with about 7% up and down. And when we are saying 7% up and down in level fluctuating for 18 meter cube, it is significant and reasonable to cause carryover of liquid or two-phase flow with this saturated steam, which caused or escalated the erosion or corrosion phenomena. High water entrainment from the saturator led to wet steam and two-phase flow, which escalate erosion and corrosion. Erosion marks were observed on bottom plate of the saturator drum, which was overcome with batch plate. Mist eliminator found damaged adjoining the steam outlet nozzle, which is here. This is the mist eliminator. No thickness loss, first of all, was observed on the superheated steam line coming from the extraction of steam turbine. No thickness loss also was observed on the steam condensate line coming back from the stripper shell side. Open inspection of steam distributor, it was found that the distributor holes were found unevenly enlarged and badly eroded. Actual number of holes of 20 millimeter, which is the design size or diameter, were counted as 120 as per the inspection, while according to the design data sheet, it should be 360 holes with 20 mm diameter. Enlargement of bottom distributor holes, more than half of the holes found enlarged in the range of 34 to 52 millimeter. Against the design 20 millimeter. This leads to improper distribution of extraction steam over the length of the steam saturator, which caused the level fluctuating and the carryover of the condensate with the steam. What we recommended two recommendations. First of all, to modify the design of the distributor or the pipe distributor holes according to the process sensor feedback, and it was increased to 400 holes. Second recommendation, to tune the level transmitter and to ensure that there is no level fluctuating in the drum. Conclusion, less number of holes in the pipe distributor caused this high velocity of the steam release at the bottom steam saturator drum, and irregular enlargement of holes caused water level fluctuating. This water level fluctuating and the high speed of steam caused high water droplets, entrainments from steam saturator, escalated corrosion and erosion phenomena, and the leakage. The present conditions now, alhamdulillah, steam pipe distributor has been replaced with STAMI carbon recommended design to 400 number of holes with 20 millimeter diameter or pitch. Saturator drum to V905 level now is constant. Whole steam line, saturated steam going from the steam drum or saturator drum to HB stripper has been replaced. Future plan to avoid the reoccurrence, first of all, we will replace steam saturator drum totally. We will revalidate the original design with the actual design, and also we will enhance the inspection scope for doing the equipment internal inspection. That was the case. Thank you for listening. Any question?